I'd like to do an example, which is two blocks sliding down an incline. They each have different coefficients of friction, and the coefficient of friction of A is larger than B. What that means is that then the blocks stay together. Now this is kind of a long problem. It's pretty complicated and it takes a little bit of effort to get all the way through, but it has so much good stuff going for it. I really like this problem. Also, this problem and I have a little bit of a history, and I'll tell you about it at the end, and I hope it has a really cool, kind of a neat lesson. I want to find out what the acceleration of the system is. The physics that applies, I'm sure, is going to be the forces, so I want to do a Newton's law analysis on this system. So first of all I have to do is choose an object. I'm going to choose A first, and I need to find the forces on A. Okay, so there's going to be gravity is going to be a force. Now there's two items then in contact with A. That's block B and then the ground. There isn't going to be friction. There's no motion of the surfaces relative to A and B, so I don't need any frictional force there. But the contact force between the ground and A, I'm going to break up into a normal force and then the frictional force. Given those four forces, I can now do a free body diagram. So when I do a free body diagram for something on an incline, the coordinate system parallel and perpendicular to the ground, and then the coordinate system parallel and perpendicular to the ledge, which means this angle there is theta. That's this angle theta. And then once I have that theta, I can identify all the others. I'm going to identify my positive x direction here and my positive y direction here. The key, though, of course, is to put the x coordinate along the incline, along the direction of motion. The whole system then is moving in the positive x direction. So as long as all the motion is in one dimension, I want to make sure one of my axes is in that dimension. I have the force due to gravity straight down. The normal force of the block on A is perpendicular to the surfaces between the objects and from the agent to the object. The normal force of the ground on A, well, that's perpendicular to the surfaces. And then the frictional force then is parallel to the surface. I know it's pointing in the negative x direction because the whole system is moving in the positive x. The frictional force is opposing the motion of the object relative to the agent. The object is moving in the plus x relative to the agent, so the force due to friction is in the negative x direction. So now I want to sum all of these forces. And so my force due to gravity is not along one of my coordinate axes, so I have to find the components. So I draw lines from the tip of my gravitational force to the two axes such that they make a right triangle. I want to find the x component. The length of that segment is going to be the magnitude of the force, which is ma times g. That's the magnitude of the gravitational force on A. And it's going to be sine theta. This is I hat, and it's in the positive I hat direction. So now I need to find the y component. So that's going to be the length of that triangle, which is then the magnitude of the force, mag cos theta, j hat. And looking at my coordinate system, I can see if that's positive, then this direction is negative y, so this is in the negative y direction. Again, I always go to the coordinate system to see which is positive and negative. Okay, so that's the gravitational force. Next is the normal force of the ground on A. So it has nothing in the x direction. And it has its entire magnitude, n sub A, in the y direction, and it's along the positive from my coordinate system here. It's in the positive y-axis. So now that gives me my frictional force on A, and it has a magnitude equal to the coefficient of friction between the ground and A and the normal force on A. That's from our contact force model. And it is along the x-axis, but, of course, given my coordinate system, this is negative x, so it's along it has the entire magnitude along the negative x direction and then it has nothing in the y direction. So then finally, here's I'll get the normal force of B on A. It exists here, which is entirely along the positive x direction. So it has some magnitude I plus 0j, and it's positive. Here's the sum of all these forces. The sum of all of these forces is equal to the mass of A times the acceleration of A. And so we know that the object, as we set up our coordinate system, only has an acceleration along the positive x direction, which is why we set the x along the direction of motion. So this would be true. We only have a component along the x direction. Okay, so what does that give us? That gives us some relationships. Here we have a sum over the x components, and then a sum over the y components. And so the y component is pretty easy to see first. We have that the normal force of the ground on A is equal to the mass of A times g cos theta. Now if I look at the x components, I get that mass of A times g sine theta minus mu sub A times n sub A plus n sub B of A, the normal force of B on A, is equal to the mass of A, acceleration of A. Well, the first thing that I do here is I can substitute in for this. I'm still in the brainstorming session, but I know I can get rid of one of these unknowns just by substituting the normal force of the ground on A into the second equation. And so this gives me m sub A, the mass of A times g sine theta, minus the coefficient of friction for A times the mass of A times g times cos theta, plus the normal force of B on A is equal to the mass of A times the acceleration of A. So I'm going to give this an equation. This is, I think, an important equation. I'm going to give it the equation 1. What I don't know is the normal force of B on A and A. So I need more equations, which is fine because I have a second object that I can do a force analysis on. Okay, so where are the forces on mass B? It's the same four forces. So there's gravity. So there's the force of gravity on B. Now there's the ground contact force. So here's the normal force of the ground on B. So I'll call that N sub B. There's the frictional force of the ground on B, F sub B. And then there's the normal force of A on B. Now the normal force, the forces go from the object to the agent. So if A is the agent and B is the object, the normal force points perpendicular to the surface from the agent to the object. So it goes in the negative x direction. Okay. So that is my free body diagram, and so now I can break it up into components. So let's start with gravity again. Now I see I've got exactly the same triangles that I had before, only this time my force due to gravity is the force of gravity on B instead of A, but it's exactly the same form. So my x component is mass of B times acceleration due to gravity sine theta I hat, and the mass of B times acceleration due to gravity sine theta j hat, and I know that the y component is pointing along the negative y-axis, while the x component is pointing along the positive x-axis. So the normal force of the ground on B is again the normal force. The whole entire magnitude is along the positive y-axis like before. Now the force of friction on B is the entire magnitude, is the coefficient of friction on B times the normal force of the ground on B. That's in the I hat. It's along the x-axis, and it's in the negative x direction. And so then I have the normal force of A on B, which was right here, also in the negative x direction. So the entire magnitude in the x plus 0 plus 0. The sum of all the forces on mass B is equal to the mass of B times the acceleration of B. Again, only one object. So this is now I've set it up so the entire acceleration is along the positive x-axis plus 0 j hat. All right, so that gives me some relationships to work with. I can sum the x components of my diagram plus the y components, and that can give me some relationships to work with. So the first relationship here I have is in the y axis. I have a similar expression to what we had before. The normal force of the ground on B is equal to the mass of B times g sine theta. It's telling me that the normal force of the normal force of the ground on B is equal to the y component of the gravitational force, which I did wrong, right? It's the cosine. All right, so that's our first relationship in the y direction. And then so we have a second relationship for the x component of our F equals ma. And that gives us m sine theta, essentially the x component of the gravitational force, minus coefficient of friction B, normal of the ground on B, minus the normal force of A on B is equal to the mass of B times the acceleration of B. Again, I've got a bunch of unknowns here, but the first thing I can do is substitute in the normal force for B, like I did last time, and that gives me mass of B times g sine theta minus the coefficient of friction B times the mass of B g cos theta minus the normal force of A on B is equal to the mass of B times the acceleration of B. Okay, so here's the second important equation. So I really have 4 equations and 4 unknowns here at the moment. I have acceleration of B, the normal force of A on B. I have acceleration of A and the normal force of B on A. But the normal force by A on B is the same is a Newton's third law force pair to the normal force on B by A. And so I know that normal A and B is equal to negative the normal B on A, Newton's third law force pair. Okay. So that tells me that their magnitudes are equal. B is equal to normal BA, which is equal to the normal force. I also know that, I get a different color in here, that because the objects are always in contact with each other, that the accelerations have to be equal. So this was from Newton's third law force pair, but this is simply logical information that I extract from the context of the problem. So substituting in these into these expressions, I'll be left with only 2 equations and 2 unknowns, normal and A. Okay, so let's solve this one for this normal force. If I rewrite that down here, and so that's just solving this expression for here. I moved these on the other side, and then move these two terms on the other side, and then I'm just solving for n and a. Here I drop the subscripts on those now that I only have one. Okay, so now that I have this solved for the normal force, I can substitute it, this here, into here, and all I should have left is the acceleration, and I can solve for the acceleration. So I'm going to substitute that in. So what does this equation now look like with this equation substituted in for n? So I have m sub b g sine theta, that's just this first term, minus mu sub b m sub b g cos theta, that's this term, minus, now this whole thing, minus m sub a minus mu sub a m sub a g cos theta, plus, remember this is minus all these things, m sub a g sine theta, and all of this is equal to m sub b a. Remember this, the a's are a sub b is equal to a sub a. Oh my goodness. So, what do I do with this thing? What I'm going to do here is I'm going to combine some terms, simplify my equation so it doesn't quite look like a mess. So I have two terms here that have g cosine theta in it. I have terms that have sine theta in it, and I have my two acceleration terms I want to combine as well. So I'm going to combine all these together. I probably didn't have to use the same color for all that. Okay, so if I look at these two terms first and combine these two, I get should I come up with a new color? I combine those terms, I factor out a g sine theta, and I have mb, mass of b, plus mass of a, g sine theta. Okay. So then I'm going to combine these two terms, and these two are both negative, so I'm going to subtract, then factor out a g cosine theta, and I get mu sub b m sub b plus mu sub a m sub a g cos theta. So I factored out a negative and I factored out a g cos theta from each of these terms, leaving me the sum of the sum here times g cos theta. Okay? So in both of these, I'm going to keep my acceleration on the other side. I'm bring this on the other side of the equation, factor out the a, and I get m sub a plus m sub b is equal to the acceleration. All right, what that did here is it gave me something I can look at to see if this sort of thing makes sense to me. I'm gonna stop and study this. So what does this mean? Well, this right here is a component of the gravitational acceleration. It's sort of the total mass g sine theta. And so it's sort of a combined force term that was along the positive x-axis that's providing for the acceleration down the incline. Okay, and it's equal to the sum of both of them. Both are contributing a gravitational term that's accelerating the object down the incline. Fine. And that is being opposed by this. I mean, this is positive. The first term is positive, but this term is negative. These are all positive numbers in here. So it's being opposed by this term, which has, in it are the coefficients of friction and the mass, and they have a gravitational term in here as well. So this is the combined the combined term that contains the friction components, which are slowing the system down. This is opposing its motion. And the gravitational term minus the frictional term gives us the total mass of the system times the acceleration of the system. All of that makes sense. There's a gravitational term providing the sliding, frictional term opposing the sliding, gives me an acceleration proportional to the both masses. I can now just solve directly for A. That gives me that A then is equal to this. These sort of cancel, and I get a mass term here plus mass B. So my acceleration is equal to g sine theta minus this really kind of a complicated expression here, mu sub b m sub b plus mu sub a m sub a divided by the total masses m sub a plus m sub b times g cos theta. So if this is my answer, does this make sense? Well, first, let's look in the limit. Let's say the limit as theta goes to 0. Let's look at what happens here, these in the limits. We're checking this solution, see if it makes sense. In the limit as theta goes to 0, this second term gets larger. Cosine theta goes to 1, and this term gets smaller, theta goes to 0. So eventually, the first term equals the second as this gets smaller and the second gets larger. And then when this happens, the acceleration goes to 0, which makes sense. Let's go back up to my picture. As I lower theta, eventually the system just doesn't accelerate. The friction is strong enough to hold the system, and it won't accelerate down the incline. And that's what this is telling us. Okay, so that's good. What happens as theta goes to 90 degrees? As theta goes to 90 degrees, cosine theta goes to 0, so we just lose the second term. Sine theta goes to 1, and A is equal to G. Okay, well that's great. That's exactly what should happen. As the theta goes to 90, the two are just falling in free fall. Okay, what about the coefficients of friction? What about as they go to 0, mu A times mu B? If they both go to 0, what does that what happens then? Again, I lose this second term here. Both, if this goes to 0 and that goes to 0, then this whole second term goes to 0, and I'm left with A is equal to G sine theta, which is exactly the result that we derived originally for masses sliding down an inclined plane. So despite how complicated this was, I'm now very confident that I have the right answer. I want to highlight a couple things about this system. Despite the fact that it was very complex, I really had a straightforward solution to finding it, and it was simply our Newtonian problem-solving strategy. Adopt a object, find the forces on that object, sum the force, put that in a free body diagram, and sum the forces on that object, and then use that to create relationships between the parameters that are known and unknown. When that wasn't enough, I chose a second object, identify the forces on that object, put them in a free body diagram, sum the forces on that object, and set that equal to the mass of that object times the acceleration of that object, which give me more relationships to use. But that wasn't enough. I had to use the Newton's third law force pair to identify that the normal force of A on B was equal and opposite to the normal force of B on A. Also, I had to extract from the problem that the accelerations of the individual objects were equal to each other. That gave me another relationship. And so I had to extract logical information from the problem. The other thing that was so critical in this problem was very big pictures, so I could keep everything straight, very clear notation, so I could keep track of the normal force of the ground on B, normal force of the A on B, as well as the normal force of B on A, etc. So very good notation, very big diagrams were also critical. And then what was another important key was when I came up with some really long expression, I didn't just go with it. I rearranged it. I put terms together so I could go back to understand the physical origin of those terms, to say that what I had made sense. I had a gravitational term, a frictional term leading to an acceleration. And once I combined my terms and I realized that those terms made physical sense to me, I went ahead and solved, and then went through all the possible checks that I had to make sure I had the right answer. And so all of those are critical in solving complicated problems. Okay, so I promised a story with this problem, a short story. And the story is like this. So I assigned this as a homework problem once. And I was in a help session, and a student came to me, and they were struggling with this problem. And they showed me like 2 pages of numbers, calculation of numbers all over the place, all of this algebra, and I could not make heads or tails of what they had done. And they had just come to me with this 2 pages filled with numbers, and they said, I didn't get the right answer. What was wrong? And I do have to tell you that for when I gave this assignment, there were numbers for the masses, specific numbers for MA, MB, mu A, mu B, etc. So they had plugged those numbers, did 2 pages of calculations, did not get the right answer, and they said, well, what was wrong? Well, I could not make heads or tails of what they had done in their calculation. And also, I did not have the solution with me. And so I couldn't quite follow along with my solution to match up what they had done. And I tried for a couple minutes, and I couldn't figure it out, and I realized that, well, I had to go off and solve this problem there so that I could then try to follow the steps and see where the student went wrong. So I didn't really want to do that, and it was really kind of frustrating to me. So I want you to get this picture. The reason I'm doing this is that I don't know if you're ever in this situation, but this was the position I was in. I was forced to do a physics problem. I didn't want to do it. I wanted to get the right answer as fast as humanly possible. So I don't know if you ever find yourself in that problem, but that was it. I wasn't doing it for a class. I wasn't doing it for a lecture. I just wanted the answer. I didn't want to do it, and I wanted the answer as fast as I could. Okay, and the moral of that story is what you see in this video is what I did. I drew the picture, identified the forces, I did the free body diagram, I summed the forces equal to MA, I did it again, I identified the third law pair. When I got here, I rearranged all the terms so it looked exactly like this. And then when I solved, I did all of these checks. All of this stuff that I'm explaining in these videos, the strategy, the visualization, the brainstorm, the checking, you never plug numbers in until the very end. It's not just tedium to make you go through it. It's not just an exercise to force you to do more work. This is how really good problem solvers solve problems quickly when they need to have the right answer.